Hello, I'm Taylor Davis, and this is Lab 4 Oscillations. So, the purpose of this lab was to investigate the motion of a spring mass system with the mass oscillating in an arc. The object that we observed was the spring with a mass attached. Um, to find the object's position, we used the tracker web tool. And to develop our computational model, we used the software GlowScript. So the goal of this experiment was to determine whether the model follows the energy principle, that meaning energy is conserved within a system. And the result was the system's total energy remains constant at zero, thus representing the energy principle. So, fundamental physics concepts that were important for this experiment were Newton's second law, stating that the net force of an object is equal to the object's change in momentum over a period of time. That equation is F net equals change in momentum over change in time. Also important was the position update and the velocity update listed there. The energy principle states that the change in energy is the sum of the surroundings and thermal energy exchanged with the surroundings. Our system was the mass, the spring, and the earth. That way, everything, every force acting on the system was within the system, or acting. Yes. So here you can see that delta E for the system is zero, and all of our changes in energy should add up to zero. And then, yeah, the rest of the equations are there. Here's what the tracker app looked like. You can see we put points as on the center of mass as the object moved, and it generated oscillation looking plots on the right side where each of the points were. So we set the initial conditions on the left. We found the mass of the ball was listed in the video, and we had to find the initial position based on our tracker app, our tracker information. And then we have a couple constants, like our spring constant we had to calculate using the oscillation period, and the relaxed length of spring as well we had to calculate by using F net as a constant. So yeah, here you can see we had to edit some of the code in order to change our values as they update within the experimental model, or sorry, computational model. So you can see we updated, we set our L hat, our stretch of the spring, we set our K value, our sorry, kinetic energy value, we set our potential energy of gravity, our potential energy of the spring, and our total energy. And then on the right side, you can see we just have some standard force equations. The force of the spring, we have the force of gravity and the spring. We have the velocity and position updates, and we have the updating of the spring. So here you can see where we modeled the data. The blue line is our computational model, and the red line is our experimental model. You can see in the x position versus time, the experimental model kind of lags behind. I think that's likely due to additional forces acting on the system that we didn't account for, such as air resistance, any type of wind, or um, that friction within the spring. Not every spring is perfect, so there can be some energy loss there too. And the same goes for the Y position. You can see how the experimental model has slightly higher peaks, and that could be due to outside forces as well. So some possible error, human error in tracking the object, and in reality, the system is not isolated. So there will be work done by the system by the surroundings. Is the energy principle satisfied? Yes. As said before, the total change in energy must be zero, since it is an isolated system. In this model, although there are many different types of energies, the change in energy is consistently zero. You can see the orange line in the computational model. So here we compared the oscillation periods. In the x direction, it was 1.615 seconds, and in the y direction it was 1.525 or 1.52 seconds. And our our K value was 6.08 Newton meters, and our K value for the y direction was 6.87 Newton meters. And that's all. Thank you.